Hello, everybody. Welcome back. Today, we're going to do the last half of section 3.2, where we're learning about the derivative rule called the chain rule and a subset of that rule called the general power rule. Last time, we had done a few examples of how to use the general power rule to take the derivative of functions. So that is where we're going to pick up now. We had started with problem number 1, where the directions were find the derivative of each function. We're not doing anything with the derivative once we find it for this problem, just find the derivative of the function as it is. Now, the question that you always have to ask when taking the derivative is, what is the overall form of my function? That way you know what derivative rule applies to it. How do you start it? Well, in this one, I have my function's first a function of t instead of x, so let's make a note of that. I'm seeing t's here where instead of x's. And I have t squared plus t plus 1 divided by square root of t to the 4 minus 1. Now, overall, what is the form of this thing? Does it first and foremost look like something in parentheses to a power? Because if it did, I could start right away with using the general power rule, which is what we're learning in this section. But it doesn't quite look like something in parentheses to a power at a first glance. What it does look like to me is a fraction, something that is t squared plus t plus 1 divided by square root of t to the 4 minus 1. So since this is a fraction and it is a division first and foremost, the derivative rule that you should start with is the quotient rule, because my function is a quotient. It's a division. So we're going to start the quotient rule, and the rest of everything will fall into place from there. In a quotient rule is as follows. If you have a function that is some top f divided by some bottom g, then the quotient rule is g times f prime minus f times g prime over g squared. And so it is our job to figure out, what is f, what is g, and what's f prime and g prime, so I can use this formula. This is where I like to come over to the side and make a list. When I'm making this list, I'm going to first label what is the f function for me, what is the part of my function that's in the f spot. Well, for the quotient rule, f is always the numerator of your fraction. So my f, the top of my fraction, is t squared plus t plus 1. And don't get this f confused with the name of your function. If you like, we can rename this function, maybe call it h. That way I'm not getting the f of my quotient rule mixed up with the f of my function name. This f is the numerator, and as part of my list, if I label what f is, I have to also find f prime. We'll come back for that one. What is g? G is always, in your quotient rule, going to be the denominator of the fraction, and that includes the square root in this case. So g is the square root of t to the 4th minus 1, which, as part of my list, I'm going to have to take the derivative of g. So it would be best to go ahead and rewrite g in a more derivative-friendly format, which is to say, make the square root look like its power equivalent. It's t to the 4th minus 1 to the 1/2 power. I'm going to take the derivative of f and the derivative of g so that I can complete my list of things that I need in order to use the quotient rule. Ultimately, I want to find this formula. I want to stick all these parts in this formula as part of the quotient rule, but I have to get them first. What's f? What's f prime? What's g? What's g prime? So let's start with f. F prime, the derivative of t squared is 2t. The derivative of t is 1, just like the derivative of x is 1. And the derivative of 1 is 0. So write that in there for emphasis. For g, this looks like something in parentheses to a power. This is t to the 4th minus 1 to the 1/2 power. This is the thing that is new to me in this section. This is where I will need to do the general power rule, because it's of this form. Some function in parentheses with a power on it. t to the 4th minus 1 with a power on it. And as part of the general power rule, you may recall from last time, you have to do the power rule to the outside function, meaning if your coefficient here, the number multiplied out front is 1, you do 1 times 1/2, c times r. 1 times 1/2 is 1/2, x to the r minus 1, where 1/2 minus 1 is negative 1/2. And inside my power rule is this same inside function, t to the 4th minus 1. That doesn't change. So we have 1/2 function to the 1/2 minus 1 power. The power rule happening to the outside. The part that's new that you have to not forget is I have to multiply by the derivative of whatever is in parentheses. In this case, I'd have to multiply by the derivative of t to the 4th minus 1. Now remember, this is just me finding g prime here. When I find g prime, I'm not done. I need all of these things so I can come over here and pile them into my quotient rule. So I'm doing work off to the side here. This is 1/2 t to the 4th minus 1. 1/2 minus 1 is negative 1/2 times the derivative of t to the 4th, which is 4t cubed, and the derivative of negative 1 is 0. All right. Now, you can leave this here. This is g prime, that is the derivative. But since we're about ready to take these over and pile them into this formula, I do want to, myself personally, clean this up a tad. How about I move this up to the front, where that's 1/2 4t cubed times t to the 4th minus 1 to the negative 1/2. And then 1/2 times 4 is 2. So I get 2t cubed there times t to the 4th minus 1, negative 1/2. So this is my g prime, a little more simplified. Does make things look nicer if you're able to tidy up as you go. So these are all the parts that I'm going to need for my quotient rule. I needed f and its derivative. I need g and its derivative. Now I have all of those pieces, so I'm going to section this off a little bit. Let's come over here then and put it all in this formula for the quotient rule so that I have the derivative of h, the overall function. So since my function is called h, an appropriate derivative for this would be to call it h prime of t is g, which is this function, t to the 4th minus 1 to the 1/2, g times f prime, which is 2t plus 1, minus, and I'm about out of room here, so I'll put it below, minus f, which is t squared plus t plus 1, times g prime, which is down here, 2t cubed times t to the 4th minus 1 to the negative 1/2 power. Squeeze that in there real good. There we go. G times f prime minus f times g prime, all divided by the square of g. So there's g, t to the 4th minus 1 to the 1/2. That's g, and I'm supposed to square it. Now this is pretty intense looking. I have two terms in the numerator. I have one term with two things multiplied minus a second term here, multiplying this big thing. And between this and this, what I could do, if I wanted to simplify it down a little bit more, would be to take maybe this 2t cubed and multiply it into this factor here, distribute the 2t cubed to all those terms in there. And what you also could do is something that I showed at the end of the last video, which is to take out a greatest common factor of 2 to the 4th minus 1 to an appropriate power. I see 2 to the 4th minus 1 in both terms right there. You could take out a greatest common factor as long as it has an appropriate power on it, and simplify the top if you wanted to. So there's more we could do here to clean this up and make it look nice, but since all it's asking for is the derivative function, we're not really going to do anything with it at the moment. This is good enough for us. This is our solution, and we're going to leave it like this. 2 to the 4th minus 1 to the 1/2 times 2t plus 1 minus each of these three terms multiplied together. All divided by t to the 4th minus 1. 1/2 squared. I could simplify that a little bit. 1/2 squared. That's a power raised to a power. When you have power raised to a power, the exponents multiply. So that whole bottom right there is 2 to the 4th minus 1 to the 1/2 times 2, which is 1 power. Okay. This is where we're going to leave that one. Let's come over here to the next one. The directions are the same. Find the derivative. And for this one, I have 5t plus 4 over t squared minus 3 to the 4th power. Now I notice here that this does have a fraction in it, but my question is always, what's its overall form? What's its general form first and foremost? What jumps out to me is that, yes, this is a fraction, but this fraction is inside parentheses. So the way this is looking to me, this is fitting as a perfect match for this idea of having something in parentheses to a power. It's just that my something happens to be a fraction. I'm going to approach this as a general power rule right away. So I'm going to try to do a general power rule on that, and the rest of it will take care of itself as I get to the steps. So let's be intentional here and be careful. My function is called g, so my derivative will be g prime, and my variable is in t here, so we're going to call it g prime of t. Now, general power rule says that whenever you have your coefficient out front, in this case, my coefficient's 1, you do the power rule to the outside function. So we just pretend that that is an x there in the middle, and go, okay, c times r, 1 times 4 is 4. Same thing to the 4 minus 1 power. So instead of 4x cubed, you have 4 fraction cubed. But unfortunately, we are not done. This is the power rule part, but I have to remember, I have to multiply by what? I have to multiply by the derivative of the inside function, the derivative of the part that's in parentheses. So I have to multiply by the derivative of 5t plus 4 over t cubed minus 3. And then I have to think about, okay, how do I take the derivative of that? Well, that's a fraction. And if I'm going to take the derivative of that, I have to do a quotient rule on that. So off to the side here, as a multiplication, taking the derivative of that fella right there, that's going to be a quotient rule. So let's come over here off to the side, and let's do our little quotient rule as part of this part, taking the derivative of this fraction. So as part of the quotient rule, you always label f to be the numerator. It's 5t plus 4. And we label g to be the denominator. It's t cubed minus 3. I then have to find f prime and g prime to be able to put everything in the quotient rule formula, which I'll go ahead and write in here. The derivative of my function named g is 5t plus 4 over t cubed minus 3 cubed times, and this is where I'm going to have a quotient rule in this spot. So I'm going to symbolically write out the formula. The quotient rule goes g times f prime minus f times g prime all over the square of g. And we're over here labeling our parts so we can come over here and fill those in. So if f is 5t plus 4, f prime, the derivative of 5t is 5, and the derivative of 4 is 0. If g is t squared minus 3, the derivative of t squared is 2t. So I have all of my lists here for the quotient rule. Let's take those and plug it into that formula, the quotient rule formula. My original function g is equal to the power rule part here times the derivative of the inside function, the derivative of this fraction where I have the quotient rule. So let's put all the pieces in. G times f prime. F prime is 5. Minus f times g prime all over the square of g. G is t squared minus 3. So as part of my general power rule, I had to do a quotient rule in it. Now this is the derivative. As soon as you finally get done putting in all the pieces, this is good enough, and you can write this in as your answer. If we wanted to do anything with it, if we wanted to take the derivative again, which is called the second derivative, or if I wanted to take this and set it equal to 0 in order to solve for something, then you would have to simplify from here. So let's just think about what I might do then. What you could do, actually, is simplify the quotient rule a little bit. You could take this 5, for example, and multiply it into that minus 3 and that t squared, and you can take this 2t and do the same. You would then collect like terms, and I think what you'd find pretty quickly is there is a factor that you can combine and maybe cancel like terms, or combine like terms and then combine factors. So nice things would happen here pretty quickly if you wanted to simplify. But for the sake of time, I'll say this is enough. This is my derivative, and we'll leave it here for now. All right, so that's it for problem 1. Problem 1 was, here's a bunch of functions, take their derivative. And we said, okay, we did that. Now let's do number 2, which is giving a little bit of context with a word problem. So how might you find one of these combined composition functions, these functions where one function is plugged in another, as a word problem? So let's read this one. A manufacturer has determined that the weekly profit from the sale of X items is given by P. So P is profit and X is items. So let's keep a log here. P is profit and X is the number of items that's being sold. Items sold. It is estimated that after T days in any week, so T is the number of days, that X equals 0.5 T squared plus 5T items will have been produced. So we have a formula for the number of items. It's going to be 0.5 T squared plus 5T, where T is in days. So I have a formula to generate how many items I'll have at any given time. Anyway, let's keep reading. What is it they want me to do? It says, find the rate of change of profit with respect to time at the end of 4 days. So a lot of times when I'm reading word problems, I'll kind of skim it and go right to the end question, because that is always going to give you an idea of what it is they want you to do. And then you can kind of work backwards and piece it together. So if we go to the last sentence, it says, find the rate of change of profit. So this is where we kind of have to see some keywords and figure out what that translates to. So rate of change is one of the applications of the derivative. So if I say find the rate of change of profit, this is the same as saying find the derivative of profit. And not only that, not only do we want to find the rate of change of profit, but it says specifically at the end of 4 days. So they want me to find the derivative of profit and then plug in a number. Now this is where it starts to get interesting. For the 4 here, 4 days, that corresponds to t. So I'm supposed to be plugging in t equal 4. Supposed to find the derivative of profit and plug in t equal 4. Rate of change of profit after 4 days. But when I look at profit, I take a second check at my profit function, notice that my profit function is written in terms of x. It's negative x squared plus 280x minus 4,000. I can't plug in 4 into that because this is a t value. Profit is written in terms of x. And unfortunately, when you're dealing with the derivative, you can't just plug t into here and then plug x into there and then take the derivative. You'd end up with a constant in both cases and the derivative being 0. It just doesn't work out mathematically. So we see the profit is a function of x, and x itself is a function of t. P is a function of x is a function of t. So what we're going to do, since we can't just plug t in there and then plug x in there and take the derivative, we'd have a constant plugged in there, get a constant, get it, and then if we took the derivative, we'd get a 0. That is to say, we have to do this the hard way, because plugging it in and reverse engineering it and then taking the derivative will give you a profit of rate of change of profit at 0, which is incorrect. So I have to take x and plug it in to my profit. P is a function of x is a function of t, so I'm going to take this formula here for x and I'm going to shove it into P. We have P is negative x squared, but x is 0.5 t squared plus 5t. Negative x squared plus 280x, where x is 0.5 t squared plus 5t, minus 4,000. So this is my P with all of my x's replaced with what x is equal to. This is a classic composition where in place of one variable in the original, I took a whole nother function and plugged it in. So this is a composition of two functions. And what am I supposed to do with this? Now this, as soon as I plugged in that formula for my x's, now my variable is t. So it's no longer p of x. I now have my profit function written in terms of t, where t is my variable. So we're getting where we need to go. Let's pretend for a second that I took t equal 4. I can plug it in here now and get the profit after 4 days, because now profit is a function of t. But since they're asking for the rate of change of profit, I have to take the derivative. So let's take the derivative of p. Now this part right here, when we look at the profit function, I have 3 terms. I have 1, 2, 3. And I can do different things to each one. So why don't I first, before I take the derivative, try to clean this up a little bit. Let's say I take this 280 and multiply it in to the 0.5 t squared and the 5t. We're just going to try to make my profit function look a little bit nicer first before I take the derivative. And then I will take the derivative. So 280 times 0.5 is 140, and I have 140 t squared. 280 times 5, let me get my calculator out for that one. 280 times 5 is 1,400. Multiply that to that, and to that, and I have minus 4,000 here. So this is my profit function. I have not taken the derivative yet. I wanted to make it look a little bit nicer first. Okay, so now I want to take the derivative. This gives you profit at NET, but I want rate of change of profit. So I've got to take the derivative. Now I have a few terms here. These terms look like regular polynomial terms, so I can take the derivative of those one at a time. That'll be nice. This part looks like something in parentheses raised to a power, and the power is 2. So I can use a general power rule on this one to take the derivative. My coefficient is -1 due to that negative sign. So I do the power rule. -1 times 2 is -2. Leave the inside alone. To the 2 minus 1 power. There's my power rule. Now don't forget that when you do the general power rule, you also have to multiply by the derivative of whatever part's in parentheses. So we'll complete that in the next line. General power rule, you do the power rule. -1 times 2, same thing, the 2 minus 1 power. That's the power rule part. Then we tack on the chain rule part, where we take the derivative of the inside function, derivative of 0.5t squared plus 5t. So we'll do that in the next line. Now let's scooch over here to my 140t squared. I'm going to take the derivative of that. That's a power rule. 140 times 2 is 280. T to the 2 minus 1. So I get 280t. Now I forgot here, it looks like when I was multiplying in my 280 times 0.5t squared is 140t squared. 280 times 5t is 1400t. Got my t there. Doesn't go anywhere. It's still there. And then my minus 4000 goes down. Okay. So the derivative of 140t squared is 280t. And the derivative of 1400t is 1400. The derivative of 4000 is 0. So I'll write that there for emphasis. So we get to the derivative. One last step, I've got to finish my chain rule part. My general power rule part. The derivative of 0.5t squared plus 5t. The derivative of my inside function. This would be a power rule. 0.5 times 2 is 1. So you have 1t to the 2 minus 1. And the derivative of 5t is 0. So this is what we get, all said and done, for my derivative of profit. Now the question is, are we done? And the answer here is not quite. I was supposed to find the derivative, the rate of change of profit, but they did say that I was supposed to find the profit specifically at 4 days. So that means I'm supposed to plug in p equal 4. So now that you have the derivative of profit function, the marginal profit function, then you plug in 4. Everywhere you see t. Now this is, you have to be careful plugging this in your calculator. Plus 280 times 4 plus 1400. So this would be -2.5 times 4 squared, which is 0.5 times 16. So that's 8 plus 20. So you have -2 times 28 times 4 plus 5, which is 9. So all those are getting multiplied together. Plus 280 times 4, which is 1400. Or sorry, 280 times 4 is 1120. There we go. 1120 plus 1400. And when you punch this out real quick, let's see what we get. All right, there you can see that better now. Minus 2 times 28 times 9 plus 280 times 4 plus 1400, 2016. So I get that P prime of 4 is 2016. Now this is a rate of change. And this is profit. Specifically, it's marginal profit. Remember from section 2.9 that the derivative of profit is called the marginal profit function. But we take 4 and we're plugging it into the derivative of profit and we get 2016. Now this is a rate. This is money since this is profit. So this is $2,016 and my variable is T. So this is dollars per unit time. So dollars per day. So at the end of the 4th day, when T is 4, my profit is changing by positive $2,016 a day. That is, the rate of the profit is increasing by $2,016 a day. That is the answer to number 2. That is the rate of change of profit with respect to time at the end of 4 days. So if we kind of zoom back out and look at the bigger picture, let's kind of summarize everything. We were given a profit function written in terms of x, but x itself was a function of t. Since they want me to find the rate of change, I have to go through the motions of plugging in the x function into both locations and then taking the derivative using the chain rule. It would be mathematically incorrect to try to take this, plug it in, then take the derivative after plugging it in again. You would end up with 0 along the way, and it just doesn't work out mathematically. So that is to say, we have to do it the long way of taking my function x, plugging it in, and then taking the derivative using appropriate derivative rules. But we get there. Just be careful and plug in your number. We get $2,016 a day. This leads us to the last bit of the section, which we go back to the chain rule. Now, I'd mentioned before several times that the general power rule, which we've been using a lot, which applies to something in parentheses to a power, is under the umbrella of the chain rule. That's because the general power rule is a very specific type of composition, but not every type of function plugged into another is going to look like something in parentheses to a power. For all other cases of two functions being composed, you'd have to use the chain rule. It's a more broad rule, but the general power rule is a very specific look and feel to my composed functions. So what does it look like if we want to take the derivative of a composition of functions when we don't exactly know what the functions themselves are? So let's go back to the very front page of this section. Down at the bottom where I talked about the general power rule, which we've practiced a lot. But then I said it was a subset of the chain rule, and I said we'd come back for this. The way that the chain rule works is if you have two functions that are composed, that is, in this particular notation, the function g is plugged inside of f. Then the derivative of such a composition is you take the derivative of the outside function, f prime, you leave the inside alone, and then you multiply by the derivative of the inside. That is exactly what we did every time when we did the general power rule. So let's revisit this generic rule for doing the problem in the back. So I'm going to copy this down at the top. It says, use the table below to find the value of each of the following. And then there's some examples of how to interpret the table. So let's look at what they're first asking. It says, find h prime of 2 if h equals f of g of x. So let's take apart the directions. When it says find h prime of 2, that means you have to first find h prime, find the derivative of h, and then plug in 2, right? X is 2. That's ultimately what we're going to need to do. But then we go, okay, I'm going to take the derivative of h then. And then I look at h, and there it is. If you notice, they didn't actually give me the functions. I'm not entirely sure what h equals. All they're telling me is that my function h has a function f with a g plugged in it. That's all I know. But what I do know is based off of this format that this is a composition of two functions. The function g is inside the f. It's not being multiplied by the f. It's straight up being plugged in inside the f. When this happens and I notice a composition, if I'm going to take the derivative of anything that looks like a composition and I don't know what those functions are, I don't know what g is, I don't know what f is, I'm going to use the chain rule. Now, technically, we've been doing the chain rule the whole time, each time that we've done the general power rule, because again, the general power rule is a subset of the chain rule. But the chain rule formula that we're going to use now is the very, very generic rule, which I had on the front page. Now, the chain rule that we had written out was that if y was a composition f of g of x, then it has to be that y prime was f prime of g of x times g prime of x. That's the formula from the front page. Copying here for ease of access. So if this is my h, and I'm supposed to be taking the derivative of it and plugging in 2, we go, okay, my h looks an awful lot like my chain rule formula, f of g of x. This is exactly what my function looks like. So how do I know what h prime of x is? Well, since I don't know what f and g is, all I can say is that h prime is that, the formula. So we copy the formula down. H prime is f prime of g of x times g prime of x. Now let's say that again. H is a composition of two functions, f and g, but I don't know what f and g are. So I can't actually find f prime or g prime in order to multiply them and make this formula a little more concrete and useful. So if I don't know what f is and I don't know what g is, but yet they're still telling me to take the derivative of this thing, all you can do is say the derivative is the formula, and we copy the formula down. So as far as we know, this is all we can say. If h is f of g of x, then h prime is the chain rule formula. We just don't know what any of the rest of this is. But this is where the table comes in, because my next mission was to do what? Find h prime, and then I'm supposed to be plugging in 2. But how do you plug in a number into a function that you can't even see? I don't know what f is. I don't know what g is. How do I plug in 2? Well, you can still. So the answer to that is everywhere you symbolically see x, like g of x, g prime of x, you plug in 2. That becomes f prime g of 2. Every x turns into a 2. And this is where the table comes in, because I actually can get myself out of this hole and find a value for h prime of 2, even if I don't know what f and g are. So let's take a look at this table. How am I supposed to interpret it? The way this table works is it has the x values in this column. X is 1, 2, and 3. And it has the functions in the top, f prime, g prime, f, and g. And the way that you should read it is that you pick your function in this row, say f prime of 1 is -2. G of 1 is 1. G prime of 3 is 2. F of 2 is 3. So that's examples of how you can read the table, in case there's any confusion on that. Now remember, this is what I said my derivative had to be, and I'm supposed to be plugging in x equal 2 into it, which means if I'm plugging in an x value into my derivative, I'm supposed to get a numerical value out for my derivative value, right? If you plug in a number into the derivative, you're supposed to get a number out. And the way that this is going to work for me is that even though I don't know what f prime and g prime are, like this is a mess of a formula, I can still get a number out for h prime. It's kind of neat. So let's finish this up. Now remember, this is f prime of g of 2, not f prime times g of 2. What is g of 2? Well, that is a value I can find because I have a bunch of function values up here. So this is where I go to. I'm looking at my function g. There's g. G of 2 is 3. So this is actually, instead of f prime of g of 2, it's f prime of 3 because that's what g of 2 equals. And now this is f prime of 3 times g prime of 2. So what is, let's go ahead and write out, what is g prime of 2 while we're here? Find g prime column. There it is. G prime of 2 is 1. We're almost there. We have f prime of 3 times 1. What this h prime of 2 is going to equal. F prime of 3 is -1. So find the f prime column, go to 3. F prime of 3 is -1. So we have -1. This whole thing here is -1. -1 times 1 means h prime of 2 is -1. Let me write that over here as a conclusion. We actually get a numerical value out for h prime of 2, even though we didn't know exactly what f and g were. We didn't know exactly what h looked like, but we still applied the chain rule formula and got a value out for h prime of 2. So let's do this again, where I don't explain it so much this time. Let's say I have h of x is again f of g of x. And they want me to find h prime of 1. And then I go, okay, that means that I have to find h prime first, find the derivative function h prime, and then plug in what? Plug in the x value in the parentheses, which is 1. So first I have to find h prime, and then I go, okay, where's h? There's h. H is f of g of x. And then we see, again, okay, they didn't actually tell me what h was. They just said it's a composition of two functions that we don't know. We don't know f, we don't know g, so we don't actually know what h is. And then we go, okay, if that's the composition, I have a rule that matches that formula exactly. My chain rule formula was, if I have f of g of x, the derivative is given by that formula, which is exactly what I have. If I have f of g of x, then the derivative is that formula. So I'm just going to take that formula and say, okay, that's what h has to be. The derivative of h has to equal this derivative formula. And there's not anything more we can say about it. If we don't know what f and g is, there's no way for us to know what f prime and g prime are in order to make this formula any more useful. So all we can do is just copy down what the formula is and say, well, if you don't tell me what h is, I can't tell you what h prime is. It's just that. And then we aren't done. So despite the fact that I don't exactly have a function, a tangible value for f and g, or f prime and g prime, I can still plug in my x equal 1. H prime of 1 is everywhere you see x, right there and there. Plug in 1. F prime g of 1 times g prime of 1. And this is where we kind of start on the inside and work our way out. We're going to try to dig ourselves out of our hole here. This is f prime of g of 1. So let's start off figuring out, okay, what is g of 1? That is actually a number that I can find because they gave me data in a table. G of 1. There's g. G of x equal 1 is 1. So this becomes f prime of 1 because that's what g of 1 is equal to. Times, what is g prime of 1? G prime of 1 is 3. So we have a multiplication here. We have f prime of 1 times 3. So let's find f prime of 1. F prime of 1 is negative 2. This becomes negative 2 times 3, which is negative 6. So that is to say that h prime of 1 is negative 6. The derivative of h at x equal 1 is negative 6. Kind of nice. I can still find a numerical value out for my derivative at that x value, even though I didn't exactly know what h was. I just knew it was a composition of two functions. So let's do the last one here. It says find h prime of 2 if h of x is g of f of x. Now let's look at this and compare it with part A. This one asked for h prime of 2, and so did this one. But what is the difference between these two? The difference is that h here is f of g of x, and here it's g of f of x. They switched them. So instead of f being on the outside, it's now g. So that means that if I'm going to find the derivative of h in order to plug in 2, find h prime of x and plug in x equal 2. If I'm going to do that, this formula up here doesn't quite match anymore. In order for this chain rule formula to work, my original function was supposed to look like f of g of x, and it doesn't. Mine looks like g of f of x. They switched them. So if they switch the order on me for my function, I should switch the order of f and g in my derivative rule, and it'll still work. So everywhere you see an f, put in a g, and everywhere you see a g, plug in an f. If they invert the composition, you invert the derivative rule formula. I'm going to write in h prime of x is, instead of f prime, it becomes g prime. Instead of g of x, it becomes f of x. And instead of g prime, it becomes f prime. It's still the chain rule, except we had to make up for the fact that they switched the order of f and g on me. So if they switch the order of f and g, that means you have to switch the order of f of g in your chain rule formula. And we did. We're here. So now that we've got the switched chain rule formula, because my g and f were switched, now I plug in my 2. H prime of 2 becomes g prime of f of 2. So everywhere you see x, plug in 2. Times f prime of 2. Now let's start finding values. What is f of 2? We look at our table for that. Let's go to the f column. F of 2 is 3. So instead of g prime of f of 2, that becomes g prime of 3, because that's what f of 2 equals. While we're at it, let's find f prime of 2. F prime of 2 is 2. So that whole thing is 2. We're almost there. Now I've got to find g prime of 3. This whole value right here, g prime of 3. G prime of 3 is 2. So we put in 2 for that. We get 2. Oh, yep. 2 times 2, which is 4. And then we're done. We found that h prime of 2 is 4. We found a numerical value for the derivative of h at 2, even though we didn't exactly know what h was, since we didn't know what f and g were. This is a symbolic chain rule. We're doing the derivative rule without knowing what the functions are. All right, that is it for section 3.2. Good luck, and we'll see you next time.